Welcome back. In this mini lesson we will derive the variance of the mean value of the result calculated by the basic Monte Carlo simulation that we introduced in the previous lecture as the simple sampling technique. The variance of the mean value is a very important piece of information for us because it denotes the precision with which the result is calculated by the Monte Carlo simulation. Let me demonstrate this on a simple example. Let's take again the problem of calculating the distance that the fission neutrons fly to the first collision. And let's assume that we have two cases. In the first one we will have very good statistics. So for instance we will sample the distance by 1 million neutrons. And in the second case we will use very poor statistics. We will use only 100 neutrons during the Monte Carlo simulation. So let's have a look at the case with the poor statistics first. So we simulate only 100 neutrons during the Monte Carlo simulation. So let me draw the axis for the distance. Let's assume that the correct result is 10 centimeters. 10 centimeters. So this is the expectation value of the distance the fission neutrons fly to the first collision. So as we explained in the previous mini lesson, we cannot calculate this number precisely during the Monte Carlo simulation. We can only estimate it. So the result will contain an error. We will estimate the result by averaging all the samples that we collect during the Monte Carlo simulation. So in this case we will average the value over 100 samples, and the result that we calculate as the mean value will therefore contain an error. So the result may be, so let's say this is 9 centimeters. When we repeat the simulation again with another sequence of random numbers, when we start the random number generator with another seed, we will obtain a different result. The error will be different. Now we already know that the average values that we calculate will be distributed normally around the expectation value, around this point. So the next result may fall, for instance, here, right? If we repeat the simulation again, it may fall here. The other simulation may give result smaller than 9 centimeters, and so on. Now if we calculate the distribution for these values, for the mean values of the distance, we will have a distribution around the expectation value. Now if we knew the variance with which we calculate these results, the mean values of our distance, then we would have enough information to estimate the error, the difference between the correct value, the expectation value, and the estimated expectation value, the mean value of our data. Let's have a look at the other case with the good statistics when we simulate 1 million neutrons during each Monte Carlo simulation. So in this case the expectation value of course is the same, the problem is the same, so let's say we still have the same correct result here. However, because the result and the mean value that is averaged over all the samples is now averaged over 1 million values, then the error in it will be much smaller than in the case when the result was averaged over 100 samples only. So in this case, the results will all fall much closer to the real expectation value. They will be distributed much closer. So this distribution of the results of the mean values of the distance will have a much narrower distribution around the true expectation value. So the Monte Carlo simulations with better statistics will give us results with smaller variance of the mean value in the result. So in order to be able to evaluate the precision of the result, we need to know the variance of the mean value of our result. So we used to denote the result by y. In this case, y is the distance. So we are going to calculate this value. Don't get scared now. The derivation may look a little bit wild, but the result will be very elegant. So we want to calculate the variance of the mean value. The mean value is a random variable. So let's just use the definition for variance of random variables. We have defined it as the expectation value of a square of the difference between the random variable, which is the mean value of the result, and its expectation value. The mean value is calculated by averaging all the samples collected during the Monte Carlo simulation. So we sum up all the samples of the result, for instance the distance between collision, and divide it by the number of samples collected. Now let's multiply and divide the expectation value by n. So I'm going to divide it by n, and I'm going to multiply it by n as well. Now when I multiply the expectation value by n, then it's the same as if I sum up the expectation value n times. Now I can move the sum to the numerator here, and I can combine both terms into one with the common denominator, and I can combine these two terms into the sum. Now I'm going to denote this difference between the actual sample and the expectation value by psi I. The n, the number of samples, is a constant, so I can take it out of the brackets. And now I'm going to expand this square term. So this one is a product of two brackets, psi1 plus psi2 plus until psi n times the same bracket. And now I will multiply each term in the first bracket with each term in the second bracket. So in the result there will be products of term psi1 squared plus psi2 squared plus psi3 squared plus until psi n squared. So we can group these terms into this result. And then there will be many cross terms, for instance those which will multiply xi2 with xi1 and so on. So these can be represented by these results here, and there will be n of these terms in total. So to progress further, let's now try to evaluate this expectation value of this square of xi and this expectation value of all these cross terms. Xi is the difference between the sampled value by the ith neutron, for instance. In our case it may be the distance to the first collision of the ith neutron, and the correct expectation value. These samples, they fall around the expectation value. Therefore, the difference between the sampled value and the expectation value may be positive or negative. So the product of xi and xi plus 1 may also be positive or negative, because xi may be positive or negative and xi plus 1 may also be positive or negative. So for instance, if we have both positive values, then the product is positive. If the both values are negative, the product is negative. But it can happen that xi is positive and xi plus 1 is negative. So in that case the product is negative. It would also be negative when xi would be negative and xi plus 1 would be positive. So if you were running a Monte Carlo simulations, you would be evaluating this product, you would see that it would be positive or negative with the same probability. So if you, for instance, draw its distribution, it would fall around 0. So you would be getting the values of this cross term around 0. So it will be normally distributed around 0. So we can say that the expectation value of this product is 0. And it should not be surprising that all these cross terms have expectation value 0, assuming that the terms within the cross terms are not correlated. So if they were correlated, then that would mean that if for instance in this case, the xi was negative, then xi plus 2 would likely be also negative. However, the samples in standard Monte Carlo simulations are not correlated to each other, and we are sure to say that these cross terms have 0 expectation value. So in fact we can remove all the cross terms from this equation. Nevertheless, this term, the square of xi must remain, because its expectation value surely is not 0. When xi is negative, then its square is positive. When xi is positive, its square is positive as well. So the expectation value of xi squared is surely a positive number, and it needs to remain here. So the final solution for the variance of the mean value of our result is simplified to this simple term. So this is our result. It can be simplified. We can use the same trick from the previous slide. We can substitute the summation with the product. So if you sum up a term n times, then it's the same as if you multiply the term by n. We can really do this operation because the expectation value of the square of all the xi's are the same in the simulation. Now we can eliminate n from the numerator and 1n from the denominator. So this is equal to the expectation value of xi squared divided by n. Now the index here is not important anymore, so I will not write it there. And this we can further write as the expectation value of the difference of the sample of the random variable and its expectation value of the random variable squared. Now when you look at the numerator here, you will recognize that this is the definition for the variance of the random variable y. So we can write it here. So the result is extremely elegant. We can easily calculate the variance of the random variable during the Monte Carlo simulation. When we sample the result, we will get a bunch of values. We can calculate the mean value and the variance of this sample. So we can easily calculate the variance of the mean value by dividing the variance of the random variable by the number of samples that we collected during the Monte Carlo simulation. Now, for the same reason for which we can never know the true expectation value for a result in Monte Carlo simulations, for the same reason we cannot know the true value of the variance in the result. So therefore we will never know the true value of the variance in the mean value of our result either. However, we can estimate the variance in the random variable by this formula, assuming that we collect sufficient number of samples when n is large. Then this formula will give us a very good estimation of the variance in the random variable. In one of the mini lessons in which I derived the variance, I also derived the final form for the variance in a similar form like this one. This formula is very useful when you calculate the variance of the random variable during the actual simulation. You can update these terms every time you obtain a new sample yi. So you simply can keep this sum as one quantity in your program and increase its value by the yi squared every time you obtain a new value. And the same you can also do here, because the mean value of the random variable is the sum of all the values divided by n. So you can do this division by n at the very end of the Monte Carlo simulation, right? You keep the sum of the squares and the sum of the samples, and then you divide both terms by n at the very end of the simulation. So this way you can estimate the variance of the random value very easily. It would be more complicated if you wanted to use this form, because every time you would generate the sample, you would have to recalculate the mean value of all these samples. So there would be extra computing time lost in order to calculate the mean value. If you use this formula, you don't have to. You can calculate the mean value only at the very end of the simulation. So here is our summary. The estimated variance in the mean value of the result is equal to the estimated variance in the actual random variable divided by the number of samples. And I forgot to stress at the beginning of this slide that the S here denotes the estimation of the standard deviation, so the S squared is the estimated variance. And that is all for now, and I wish you have a nice day.